All right, let's begin. Hope you guys had a good weekend. Happy Monday. I guess it's week 3, Monday. Wanted to pick up and just cover a couple things from Friday's lecture that I didn't get to cover in as much detail. So in Friday's lecture, I showed you kind of these plots, and what these plots represented was kind of the cross between your OLS contours. So these are the OLS contours, meaning you can have, so remember, we are fitting a linear regression model. The true relationship in our linear regression model is, where are we going? Okay, the true relationship is that our output t depends on x1 with a coefficient of 1.5 and depends on x2 with a coefficient of 0.5. And we added some random noise, so this kind of relationship isn't detected perfectly. Right now, using OLS, our best estimates are 1.458 and 0.4533. And this represents kind of the contour plots that show, where that minimum value is. And so this minimum value is when we have W1, the first slope, the slope for x1 on the x-axis here, and that's going to be 1.4588, and then W2 is around 0.45, whatever it was. Okay, right there. So that's the minimum. And these are the contours, meaning if you picked a different value for W1 or W2, you're going to get more error, and the farther away you move from that, you're going to get more and more error. We've modified the loss function so that we have now the combination of OLS plus the penalty term. Okay, and so the L1 penalty are these concentric diamonds. And so basically you have the L, which is these ellipses, plus the diamonds together. And when you kind of blend them together, you get this kind of hybrid-looking, these hybrid-looking contours. And so you start to see, as we add a greater and greater penalty, now we're getting a cross between those diamonds and ellipses here. And so this red dot represented the value of W1 and W2 that minimized OLS, which was around 1.45 and 0.45 whatever for W2. But now that we've modified the loss function, the set of parameters that minimize the combination of OLS plus the lasso penalty is now closer to like 1.1 and 0.1. or something like that, this blue dot right here. And if you increase it enough, it pushes the W2 all the way down to 0. So this is now close to like 0.998 for W1 and 0 for W2. This is, at this point, we've increased the penalty so much that one of those coefficients shrank down to 0. And as we continue to increase the penalty, it pushes this blue dot towards 0. Okay, eventually we're saying there's so much penalty applied to any of these coefficients that the value that's going to minimize the loss function is going to be 0, 0. Okay, that as soon as we start increasing, changing what W1 or W2 is, the penalty grows so much that it doesn't improve the loss function. Okay. Similar kind of thing with ridge regression. In ridge regression, this component that we're adding, there should be a squared here, is the L2, the sum of the squares, which is basically these concentric circles. And so we have a blend between ellipses and circles. And as I increase the lambda here, we get, the contours look more and more like circles centered around the origin, okay? And what we notice is that this blue dot kind of shifts away from the OLS solution. The OLS solution is right here at the red dot, and as I increase the amount of penalty applied to the size of the coefficients, then the blue dot kind of moves away from that. We see it move toward this line, W1 equal to W2. And once they kind of approach each other in size, then they start shrinking down together. And here with lambda, a really big number, it shrunk it down quite a bit, but not quite to 0. And so I wrote kind of my observations there. Another way you can think about what you're trying to minimize in ridge regression is you can also think of them as trying to minimize our residual sum of squares subject to a constraint. Okay, so if you think about Lagrange multipliers, if I go back to what is the, our loss function, so our loss function, this is basically residual sum of squares plus lambda times something over here, okay? And that something over there is either the sum of the coefficients squared, here they're betas instead of w's, or the sum of the coefficients, absolute values of the coefficients. And these are kind of like, you can think of these as Lagrange multipliers, and these are the constraints, right? So when you use a Lagrange multiplier, it's basically the function that you want to minimize plus lambda times, the constraint here, okay? And so here we're just kind of applying to some kind of constraint over here. Either the constraints are a sum of beta squares, or the w squared, or the sum of the absolute value squared, okay? And so if you think about, okay, what do those pictures look like? Some of the absolute values, those constraints are basically diamonds over here. And then over here for ridge regression, the constraints are basically circles. And so you can also think of this as having your OLS function, which is just a bunch of concentric ellipses, right? Here the ellipses are, pointing in a different direction, but you got these concentric ellipses, and the solution is going to be where the constraint intersects the ellipses. So this is just another way to kind of think about it, right? So, these things are just kind of what happens when you add the ellipses plus the concentric circles or the diamonds, and you get these funny looking contours. Another way to think of this as you've got these concentric ellipses, and then you have the constraints, either diamonds or circles, and you're looking at the intersection between them. And basically where they cross, that's going to be your solution. One of the reasons why we want to do regularization, okay, is because it helps us avoid overfitting. And the way, the mechanism in which it helps us avoid overfitting is that it reduces the variance of our parameter estimates. So, whatever W we end up selecting, basically the slope that we use for our x1 or our x2 or whatever it is, we're reducing the amount of variance, right? And so what do I mean by the amount of variance, okay? Well, if you think about just plain old ordinary least squares regression, we take into account that the data we see has random noise built in. Okay, so in your linear regression class, one of your assumptions is that the random noise is normally distributed, right? So after you fit your line, you check your residuals, and you want to see, do my residuals look like they're normally distributed? Because that's kind of one of the key assumptions, is that there's noise in the actual observations that we're observing. And so if we think about that, if you go out and gather a set of data, you can fit linear regression to it, and you'll get a slope value, right? And if somebody else says, I want to do the same exact thing, and they go out and they do a random sample of the population, and they get another set of data, right? Their slope is going to be different from your slope, because their observed data is different from your observed data. So even if you're trying to study the same phenomenon, because you have different random samples of data, you end up with slightly different parameter estimates, right? Their slope and intercept estimates will be slightly different from your slope and intercept parameter estimates. But if their slope estimate and your slope estimate are pretty close to each other, right? Like let's say your slope is like 5.1 and their slope is 5.12, you'd feel pretty good about that, right? You'd feel like, okay, my slope and your slope, we're getting something pretty close. This feels pretty good. Okay. However, if you're trying to estimate, what's the effect of, I don't know, just some variable. Okay. Like, did you guys use like the housing data set in 101A? I don't know. What kind of data sets do you use in 101A? You didn't use data. No? All right. Well, okay. So in a housing data set, you might have like one of the variables might be like bedrooms, right? Number of bedrooms on the final cost of the house. And you're going to find positive correlation. More bedrooms in the house, it's going to cost more. And so, one person looks at a random data set and they say, hey, you know what? Every bedroom you add, the cost of the house goes up $40,000. I don't know, I'm making that up. Okay. Somebody else says, oh, no. You add the bedroom and the cost only goes up $20,000. Okay. Or somebody else says, oh, no, bedrooms have a much bigger impact. Every additional bedroom, the cost of the house goes up $60,000. Okay. That kind of wild variability is kind of undesirable, right? And in 101A, you learn that like you end up having huge variance on your coefficients if like there's high collinearity, right? So if you have high collinearity in your variables because you have like the size of the house and the number of bedrooms are highly correlated and things like that, and so that ends up inflating the variance, and so you get this variance inflation factor because this high collinearity says, oh yeah, it's hard to tell if the true thing that's responsible for the cost is the size of the house, the square footage, or the number of bedrooms, or the number of bathrooms. These are all kind of highly correlated, so it's hard to tell what's going on. And so, one data set says, the slope should be this, and another data set says the slope should be that. So, it's undesirable if there's a huge amount of variation in these parameter estimates. And so regularization helps kind of reduce that, okay? Let me go ahead and give you your first view quiz answer. It's the letter D, D as in dog, okay? And so you're gonna just see a couple of graphs here. And this is just, I start off with this huge cloud of points. And the cloud of points represents all of the different W1 and W2 values that could be found for just different random samples of data. Okay? So remember that the true, this is, I think the true value for W1 is 1.5, and the true value for W2 is 0.5. Okay? So the true value is like right here. I didn't actually draw a dot. But because of just random noise, sometimes, you end up estimating that the value is 2.0 for W1 and 0.2 for W2. And sometimes because of the random noise, you end up estimating a value of, say 1.0 for W1 and 0.85 for W2. And all of these different little dots here represent some of the different W1 and W2 combinations for different random sets of data. Does that kind of make sense, what this cloud represents? So each dot is the result of fitting ordinary least squares regression to a different random data set, okay? Drawn from the same population. They're all drawn from the same population, but they all have different random noise, and because of the different random noise, sometimes your W1 estimate ends up a little higher, sometimes your W1 estimate ends up a little lower, sometimes your W2 is a little higher, sometimes your W2 is a little bit lower. But overall, centered around the true value of 1.5.5, okay? But you got kind of this dense cloud of points, and sometimes because of the random noise, you end up kind of extreme, but you know, that's just the nature of random noise, right? So this is what we have. And so the size of this cloud of points kind of represents the variance in our estimates, right? If we had low variance, this cloud of points will be really small. But right now with OLS, we have, you know, kind of a big amount of variance here. You guys are doing 100C right now? Have you guys talked about the BLUE? Okay. That was just recently or no? Kind of? Okay. So in 100C, you learn about how OLS is the BLUE, best linear unbiased estimator, in that it's unbiased because if you look at this cloud of points, the center of the cloud of points is going to be at the true value, okay? And if you look at any other estimators, the cloud of points is not going to get smaller than this, okay? So this is basically the smallest amount of variance. That's the best part that you can have as far as estimators go. And it's unbiased because if you look at the center of this cloud of points, it's at the true value. Okay, what is this? These red dots are basically what are my different estimates if I apply a lambda penalty. Okay, so if I apply a lambda penalty of 10, it kind of shifts all of my answers. So lambda here, this is lasso, and we are penalizing the absolute values of the coefficient estimates. And here, if I apply a larger lambda penalty, the cloud of points shifts even greater. Okay, and so you can actually see it's the exact same cloud of points, and all we're doing is we're just kind of just moving them diagonally. Okay, so this is it's like the red dots are just almost an exact shadow of the black dots, or actually they're just shifted slightly. And the orange one's also exact shadow. It's just the exact same thing, just kind of slided down. However, what happens is when it crashes into this, say this x-axis here, they just zero out. They don't cross over onto the other side because you're penalizing the absolute values. And so once you hit 0, you can't shrink that further, right? Going negative just causes the penalty to increase at that point. So it's not going to ever go negative there. Okay, and if I apply a really big penalty, then everything kind of, or a whole bunch of these dots just crash into the x-axis and become 0, or I guess the W1 axis, and become 0 here. Okay, and so, you know, if you measure the variance of this cloud of estimates, it's a lot smaller than the variance of the original cloud of estimates. Okay, and then, you know, if you apply it even further, it's hard to see, but there's a dot, and basically all of the estimates have become 0, 0. Okay, and so if I plot them all, you can just see kind of the red dots, the orange dots, the green dots, and the blue dots right here. Okay, and each of these things, basically once some of the dots start becoming 0, we're shrinking the variance in our estimates. Okay, and that's one way to kind of reduce the variance in our estimates. Similar kind of thing that happens with ridge regression, except this truly actually shrinks the variance of our estimates. Here, you can imagine placing these black dots on like a sheet of rubber, okay? And then we're gonna just, I guess right now the sheet of rubber is stretched out, and we're gonna start to let it like compress. And so it's hard to kind of see here, but this red dot, cloud of red dots, is basically the exact same as the black dots, but just kind of like compressed in, okay? And so there's like a couple like weird patterns of like dots here that you can kind of see, and if you look at it over here, it's like similar kind of weird patterns showing, okay? Similar over here, and it just gets kind of compressed even further, and then plotting them all. This is what happens when you apply different sizes of these lambda penalties. And here you can really see the variance of your parameter estimates shrink quite a bit. Okay, so if you have lambda equal to 500, there's very little variance in the estimates of what W1 and W2 are, right? So, you know, with the original OLS, when I pick a random data set and you pick a random data set, it's not that weird for you to have gotten, like, say 1.8 and 0.2, and I get, you know, 1.0 and 0.8, okay? But over here, if you and I pick a random data set, we're both going to get like the same kind of values. We're going to get like 0.43 and 0.32 or something like that, right? There's very little thing. But the problem here is this is way biased, okay? The center of this cloud of points of blue dots is way different from the original, the real solution of 1.5 and 0.5, okay? The true solution is 1.5.5, and ordinary least squares regression gets you something kind of in that ballpark, but high variance, and different amounts of penalty get you less variance, but you know, quite, you know, shift you away from that true answer. And so, looking at this this picture, I would say the red cloud of points probably outperforms any of the other ones, just because I would say these biased answers are a little bit too biased. But you know, the red dots kind of shrink the amount of variance, and so there, you know, there's a balance. You know, how much reduction in variance do you want versus how much bias you want? Okay, and that's going to be the focus of this slide deck, which is all about the bias variance trade-off. Okay, do you want your solution to be biased, or I mean, do you want your solution to be unbiased, but you might have high variance, okay, as represented by this. This is unbiased. The center of all of these dots is right here in the center where it's the true answer, 1.5.5, but you're just picking one random dot here, so you don't know if you're like the one that's pretty bad down here or the one that's pretty bad up here, or one of the okay ones kind of in the middle. You don't really know. You got high variance, right? Or, you know, you can kind of move to the other end where you have high bias. The center of these dots are way different from the true solution, but you have very low variance in your estimates, okay? Obviously, we want some kind of balance between the two. And that's kind of this concept of the bias variance trade-off. So let's go ahead and take a look at that. Okay, so I wrote the regularized loss function combines the OLS loss function with blank, and it's going to be like a penalty for complexity, okay? And then the blank term is used to determine which goal has greater priority, and that would be the lambda term, okay? So you can say which one's more important, reducing the RSS, residual sum of squares, or your mean squared error, or whatever that is, your OLS term, or reducing the complexity is more important, okay? And the lambda is going to kind of be a knob that says we really want to reduce complexity, or reducing complexity is not a huge priority, right? So if you shrink lambda down to 0, then it's the same as OLS regression, okay? But then if you blow up lambda to infinity, then the most important thing is going to be shrinking your coefficients, and your solution is going to be 0 for everything, okay? So those are the two extremes, and you know, certainly the lambda infinity is a bad one. There is something known as elastic net, which is kind of a hybrid between lasso and ridge regression. So lasso is you're adding the sum of the absolute values of your coefficients. Ridge takes the sum of the squared coefficients. And elastic net says, hey, you know what, let's add them, combine them both, okay? So it's kind of like let's add the diamonds and the circles and the ellipses, right? That's kind of what we're doing here. So we still have lambda, the ellipses, the ordinary least squares, contour lines. Now we're also adding the diamonds for the lasso, and we're also adding the circles for ridge. And we have kind of a mixing proportion, all right? So we have this, an alpha, with alpha equal to 1, it's basically all lasso, all diamonds, and 0 for the circles, okay, 0 for ridge. And if you have alpha equal to 0, it's no diamonds and all circles, okay? And you can kind of, it's kind of like this dial where, I don't know, you can imagine this dial. On one side you have diamond, and on the other side you have circle, and you're kind of like turning it, cranking it one way or another, and the shape is like kind of changing from circle into diamond back into circle or something like that, right? We can imagine this kind of like slider on an app or something, and we can imagine this kind of shape. And that's basically what's happening here. We've got alpha and 1 minus alpha here, multiplied by either of these things. For whatever mathematical reasons, this one's divided by 2, and it just works out mathematically better that way, but you know, it's still this kind of concept of switching between the diamonds and the circles, okay? And then overall, you also have this kind of lambda term that you can also go from 0 to infinity or something like that. So, yeah, just imagine, I don't know, some kind of like app where you have these different sliders or knobs that you can kind of just slide up and down and see the effect of these things. And so we have that, okay? And that's what we have. And so this combination, this is known as ElasticNet, okay? And it's implemented in this package called GLMNet, which is kind of a popular, I guess, a linear regression tool. So you can use like LM to fit linear models, and you can also use GLMNet to fit these regularized linear regression models, okay? And so this is basically text taken straight from the GLMNet documentation. And it says, you know, the ridge penalty will shrink the coefficients of correlated predictors towards each other, okay, which we kind of saw. You know, we saw them moving towards that line, W1 equals W2, while lasso tends to pick one of them and discard the others, because lasso will shrink some of them down to 0. And it says ElasticNet's kind of a penalty that mixes these two. And if you have predictors that are correlated, alpha equal to 0.5 tends to select the groups in or out together. This is kind of a higher level parameter, and users might pick a value up front or experiment with a few different values. Whenever you see something like this basically means we're not 100% sure how to give you advice on like what best number to use. So play around with it and go with what looks to be working well, right? A lot of this, you know, machine learning sounds so fancy and stuff, but a lot of it is also like guess and check, trial and error, okay? Let's see what works, because the answer is everybody's data is all messy, and it's hard to know, like, we don't have a good answer for every single data set out there, okay? Some data sets are like super nice and clean, right? Like the iris data set. You guys all know the iris data set, yeah? And that one's like so nice and clean because it's like, oh, we measured these petals and what was it? Sepals. And that's like nice, okay? But everything else other than that is so messy. So yes, we can predict iris data set pretty well. Other stuff, it's a lot harder. But you can use GLMNet. You just call library GLMNet, and you load stuff up. I also teach 101C sometimes in the summer, and then we use GLMNet, but not directly like this. I use it in the context of Tidy Models, which is a great package, and it has a Tidy Models is this is just a side note here. Tidy Models is kind of like this overarching framework, I guess, that allows you to kind of like plug in different kinds of packages and models, and one of them allows you to plug in GLMNet, and you can just kind of like write some really simple code to fit GLMNet. But anyway, if you wanted to use GLMNet directly, you would do this. You have to specify all of your predictors in an X matrix. You take all of your kind of actual values in some kind of matrix Y or vector Y, and then you say, hey, I want alpha equal to something, right? Alpha 1 is all diamonds, all lasso, no ridge regression. Alpha 0 or 0.5 or something gives you something like that, okay? Here I've generated some artificial data. Okay, I've got 4 X variables. X1 and X2 are correlated. X3 and X4 are correlated. X1 is independent of X3 and X4. X2 is also independent of X3 and X4. So you basically have these 2 predictors, X1 and X2, that are correlated and unrelated to these other 2 predictors, X3 and X4, that are correlated. The true values of Y depend only on X1 and X3, but because X1 is correlated to X2, Y is also gonna be related to X2, and because X3 is correlated to X4, Y is also gonna look like it's got some kind of relationship with X4, and so all of this is kind of generated here, and we want to kind of pick this out, and so we'll use GLMNet. This is the output of GLMNet. It's this huge mess here, okay, and it's like hard to understand. But you get these 3 columns, okay? One is this measure of degrees of freedom, one is percent deviance, and one is lambda here, okay? And what we see is that as the lambda starts off high, and as it shrinks, our percent deviance grows and grows, okay? The percentage of deviation explained is basically equal to kind of like your R-squared value. It's like your sum of squares due to the regression or sum of squares due to the model divided by your sum of squares total, okay? This degrees of freedom is basically how many additional parameters are being estimated. So at 0 means you're not estimating any parameters. This is what we call the null model. We just predict the mean for everybody, okay? So we just say, hey, what's the output of Y? Let's calculate the mean of Y, and we're gonna just predict the mean for everybody. I don't care what your X1 values are. Your prediction is just the mean, okay? And then we improve our model by saying, okay, wait, let's take into account someone's X1 value, okay? And if their X1 value is this, then we'll adjust their thing to be higher. Or if their X1 value is lower, we'll adjust their prediction to be lower, okay? And then we can continue to improve our model by saying, like, let's also take into account our X2 or X3 or X4 or something like that, right? And so every additional kind of term, every additional parameter you in there uses up an additional degree of freedom, okay? When lambda is large, the model complexity is punished greatly, okay? And so that kind of pushes all of your coefficients down to 0, and you end up having degrees of freedom 0, and we have no X predictors. As lambda decreases, the models are punished less for complexity, and this allows the models to kind of incorporate more terms, and the percentage of variance explained increases. Eventually, if lambda reaches 0, then no regularization is applied. All of your coefficients are just the same as OLS, fitting OLS. Okay, here's the OLS model. OLS, if you just did LM to your data, LM is actually able to pick out that X1 and X3 are significant and X2 and X4 are not significant, but you still end up getting kind of, you know, when you do LM, you get coefficient estimates for each of these things, but you know, you just end up getting, you know, p-values that are not significant. All right, let me give you your second view quiz answer, the letter A as an apple, okay? And so this is just what happens as we change our R-squared values, okay? So when, our lambda values, and what happens to our kind of our R-squared value. So when lambda is huge, our R-squared value is basically 0. And as we shrink our lambda, our R-squared values grow until we reach kind of the max R-squared is 0.954, I guess. I don't know. That's somewhere up here. okay? You can ask for what the coefficients are themselves. You get this kind of sparse matrix. It just kind of fills out all the values and it leaves dots. The dots basically mean 0. If you don't like seeing dots there, then you can say as.matrix and then it will actually fill in the zeros. But you know, it's the same things, but just, you know, 1.729, 0, negative 0.69, negative 0.69, and 0. Okay, so the sparse matrix is kind of easier to read at a glance, but also a little bit trickier to use when you want to like multiply things because you don't actually have values in there. You just have dots, but they're basically zeros. Okay, and the tail end of the matrix. Okay, so this sparse matrix has let's see, it starts off at S0 and goes all the way to S55. Okay, and so I've just been kind of here. I just kind of printed the first 10 columns, but it just keeps going and going until it reaches S55. At the very end, these coefficients represent like what are your coefficients when you apply a very, very, very tiny lambda penalty. And at that point, applying a very tiny lambda penalty produces coefficient estimates that are almost identical to the OLS coefficient estimates, right? So the OLS coefficient estimates are 3.04x1, negative 1.848 for x3, okay? So this is what you get when you fit LM, 3.04 and negative 1.848, okay? But OLS also kind of gets these coefficient estimates that are kind of close to 0, negative 0.01, 0.054, and things like that. That's just what happens when you just fit LM. And traditionally, if I gave you this as an LM problem, right, if you had this data set in 101A, you would look at this and you'd say, okay, well, this thing is not significant and this is not significant, so I'm going to throw them away. I'm going to refit the model using just x1 and x3. That's what you would do. Okay, but that required kind of this extra step of like first fitting all of them, looking at the thing, making some decisions, and then refitting another model. Okay, Lasso kind of, in a sense, streamlines this a tiny bit. Okay, rather than fitting the model, looking at the output, making some decisions, and then fitting another model, a revised model after that, Lasso just says, hey, you know what? Let's just fit everything to it. But we're also going to apply a penalty that's going to shrink some of these coefficients down, okay? So even with like kind of the smallest Lasso penalty, it shrinks down the coefficients for x2 and x4 down to 0, okay? So we get a coefficient for x1 and a coefficient for x3, and then a coefficient for x2 and x4 has already shrunk down to 0. Having these x2 and x4 coefficients down to 0 didn't require me to first fit the model, make some choices, and then fit the model, a reduced model. Okay, here I just fit the kind of all of the variables all at once, but I just say apply a penalty that shrinks some of these coefficients, and when we do that, it automatically just shrank them down to 0. So that's kind of one of the nice things about Lasso, and so Lasso helps out when you have like a huge data set with like 80 parameters, okay? And this might have been something you encountered in 101A. Like in 101A, you were like, okay, I have to do this tedious forward stepwise variable selection or backward stepwise variable selection, right? Where you fit all 80 models and then you look at your output and you're like, okay, now we'll fit 79 variables and then we'll get rid of the least significant one and we'll fit 78, and you kind of do this backward selection and it's like a little annoying, okay? Lasso just says, let's throw all 80 of them in there. Let's apply this penalty thing. Some of these things are going to shrink down to 0, and boom, now we're down to 16 variables or something, okay? And the other ones got shrunk down to 0. And that's kind of what's happening here. Okay, and so, and then, you know, what am I saying? Okay, if you wanted to see like, okay, what are the specific coefficients that apply, you know, when a certain particular value of lambda was used, you can do that. You can kind of specify this. You get these GLMNet also includes this kind of automatic cross-validation thing, and so what this plot is supposed to show us, it's kind of hard to see, okay? So these are different sizes of lambda, okay? It's the log of lambda, but anyway, over here, this is applying a huge amount of lambda, and it says your mean squared error is huge, okay? And then here you can kind of shrink lambda smaller, really, really small, okay? And you get less mean squared error, okay? What this line here is when the cross-validation mean squared error is minimized. If you pick whatever lambda this corresponds to, this line right here, this corresponds to where your mean squared error was minimized when you did cross-validation. Okay, so again, you know, there's variance in your estimates, and so if I took the full data set and let's say I did 5-fold cross-validation, I'm fitting it to like 80% of the data, and I'm predicting on the last 20%. Okay, so I fit it to 80% of the data, I get some slope intercept estimates, and I say, okay, use that to predict the remaining 20%. And then, and I say, how much error did I have, right? And so actually using a little bit of a lasso penalty helped out, okay? And the mean squared error is minimized when we have this. But we have a whole bunch of these lasso penalties that kind of yield very, very similar results, okay? And so cross-validation, GLMNet calculates like a little standard error and says, you know what? You can have a lasso penalty over here, and this value is not statistically significantly different from this value over here. So this is the value that minimizes everything, but this one over here is a bigger value of lambda, and yes, it does have a slightly higher mean squared error, but it is not statistically significantly different from this value over here, okay? And so our general rule of thumb is go with the largest lambda that you can go with that is not statistically significantly different from the minimum one, okay? So obviously we don't want to have huge amounts of mean squared error. This is using a lambda that's way too big, okay? We don't want that, but you know, your rule of thumb is pick the biggest lambda you can do that doesn't yield results that are statistically significantly different from the minimum, and that's what this one is over here. And you know, you don't have to like stare at the little plot and try to figure this out. There's a button you can say, hey, I want lambda min. This is the one that corresponds to the minimum, and then you can do lambda 1 SE. All right, and this is the biggest lambda that's still within one standard error of the minimum lambda. All right, and so this is kind of our the one that we would recommend here. Okay. All right. All right. So okay, I already talked a little bit about this at the beginning, talking about ordinary least squares giving us the best linear unbiased estimator, and how regularization kind of shrinks the amount of variance, okay? And overall, less variance is a desirable trait, okay? It means your model estimates, your coefficient estimates for W1, W2, or whatever it is less swayed by the noise that exists in the data, all right? If you did have things that change drastically from one random sample to another, you want to be very confident in your current set of estimates. So lower variance is a good thing, okay? The trade-off, though, is that you bring in bias. You bring in bias, okay? So here, let me, here I'm just fitting in a whole bunch of different kind of models, and these are the different kind of plots. And you're going to do something similar in your homework. So the true data, okay, the true relationship has a parameter 3 for x1 and negative 1.8 for x3, okay? true relationship. The coefficient is 3 for x1 and negative 1.8 for x3. No relationship to x2 or x4. And so these are just kind of, this is a plot of the different kinds of values that you end up getting. So when you fit OLS, the true value is centered at 3, and because of random noise, sometimes you estimate a higher x1, sometimes a lower x1, but it's unbiased, it's centered around 3. When you fit lasso, you end up, the center is not 3, it's biased. It's 2.65, 2.7, something around there. But the amount of kind of variance is a little bit less. Ridge regression, again, the center is no longer at 3, it's biased. Amount of variance you get there is that, okay? This is just kind of measures of the mean and variance for each of these things. You start to see the effect greater when the true coefficient estimate is around 0, okay? So for OLS, the true coefficient estimate is 0, but again, because of random noise, sometimes it estimates an coefficient as low as -1 or as high as 0.5. Okay, look at lasso. It's almost always going to be 0. Okay, sometimes it's a little bit higher, but most of them it got shrunk down to 0. Okay, ridge regression. The true value is 0. Ridge regression is biased and it kind of pushes that up here, but the amount of variance is a lot smaller. Okay, so ridge regression, you're going to end up getting a bunch of non-zero coefficient estimates because the penalty is the coefficient squared. So, if the true value is 0, you feel like, oh, the true value should be 0. But if it's like, I'm guessing 0.5, okay, the penalty when you do 0.5 squared is only 0.25. So it doesn't really care if you kind of like have something a little bit off, okay? And so that's what we have. Okay, these couple of slides here is kind of just this. Let me just kind of skip to the end here, okay? I fit this low S regression model, and don't worry about what low S is. The idea here is, what is the difference between bias and variance? And this is just kind of these pictures that try to illustrate how you can either end up having low variance, but you end up having high bias, okay, in the model that you fit. Or you can have very little bias, but you might end up having high variance. And the idea is we're hoping to get something in between. This red line represents the true model. So all of the data that I'm going to generate random data that's centered around this red line, okay? And so, so this is what we're going for, okay? Here, you cannot see the dots. There are gray dots, okay? There are gray dots centered around the red line, okay? And here I said, let's just fit a straight line to those gray dots. This is the best fitting straight line to those gray dots, okay? Here is, I don't know if you can see these, purple dots centered around the red line. And I said, fit a straight line to those purple dots. And here is orange dots centered around the red line. And I said, fit a straight line to the orange dots. And if you compare the blue line, the purple line, and the orange line, okay, they're all slightly different, okay, as we would expect. Okay, they all have slightly different slopes, slightly different intercepts. But if you compare them, the lines overall are kind of similar to each other, right? And here I just said, hey, let's, here's kind of a contrast. Here I have some gray dots, okay, and you can't really see them. And I told R to fit a very flexible model to those dots, and it fits them very well. It almost kind of threads every single dot perfectly, okay? Here are the purple dots, okay? And I said, fit a model to this, and again, it threads almost all of these dots perfectly. Here are the orange dots, fit a model there, okay? And you kind of have this spaghetti line, and it fits all of these dots almost perfectly. And so when you compare the three lines so far, they kind of vary quite a bit from each other, right? If we do this a whole bunch of times, I repeated this like 100 times, okay? this is what ends up happening. So the true model is this curved line in black, and I said, give me some random data and fit a straight line. Give me some random data, fit a straight line. And I repeated this process 100 times. And these are the 100 different straight lines that it fits. And then I said, hey, what's the average of all of these 100 lines? And those are these white dots in a line here. And so if you look at one line to another line, not a whole lot of variance. All of these lines look very, very similar to each other. Yeah, the slope is a tiny bit different. Yeah, the intercept's a tiny bit different. But overall, very, very similar lines to each other. Not a lot of variance. But if you look at the average of all of these things, they don't quite line up to the true model, the black line, very well. Okay. Over here, this is the result of all of the different flexible lines. Okay. The flexible lines all have wild variance from one another, right? One spaghetti looks very different from another spaghetti line. Okay. However, if you take the average of all of the spaghetti lines, the average of all of the spaghetti lines is this white dot here. What's the average of all of the different spaghetti lines right here? It's this white dot here. What's the average of all of these things? And so if you take the average of all of these things, those averages actually line up very close to the true relationship. Very low bias. But you have huge variance from one spaghetti line to another spaghetti line. Okay? So these are kind of your extremes. High bias, very low variance. High variance, very low bias. And what we're trying to go for is something that's in between. This is kind of a balance of the two extremes where you have some variance, but not too much, and an overall very low bias. So that's kind of the goal there. Okay, I'm going to go ahead and wrap it up here.